Okay, so I study babies and young children. And for most of history, when people thought about babies and young children, they thought that they were irrational and amoral and egocentric, and that they were restricted to the immediate here and now, and that they couldn't understand cause and effect. Even the great founder of cognitive development, Jean Piaget, thought that children's reasoning and thought was seriously defective in all sorts of ways. And in fact, over the last 30 years, I and my colleagues have discovered that just the opposite is true. And even the very, very youngest babies already both know more and learn more than we ever would have thought was possible in the past. And what I'm going to do today is just tell you about one study that's representative of a number of studies that we kind of stumbled across recently, where, in fact, not only have we discovered that babies and young children are incredibly smart, in some ways as smart as the best scientists, but as you'll see, in many respects, they're actually better scientists than we are, or at least they're more open-minded scientists than we are. Now, how could we, in fact, it's funny that Piero was talking about how we have no themes, but it turns out that actually some of the things that we've heard before are actually relevant to the themes of today. In fact, we've been trying more recently to figure out exactly how is it that these very young babies and young children can learn as much as they do. And what we've discovered is that they're using a technique called Bayesian inference, which is actually a technique that's often used in the kind of context of computer vision that David was talking about. And essentially, you can see this is the Reverend Bayes, and this is the baby on my book, and you can see that they have the same haircut and the same facial expression, which should make the point all by itself. But actually, what's more important is what's going on inside of the baby's head. And what's going on inside of the baby's head is this kind of set of calculations. Now let me give you just a very, very brief description of what the Bayesian idea is about, because it's really very simple. The idea is this. You have some hypothesis about what the world is like. And in fact, you have a couple of different hypotheses about what the world is like. How could you test those hypotheses? Well, the Bayesian idea is you can say to yourself, well, if hypothesis A was true, it would generate a particular pattern of data. If this were true, I'd see a particular pattern of data or evidence out there in the world. And if hypothesis B were true, I would see a particular pattern, a different pattern of data out in the world. So I'll go out into the world, I'll see what the actual pattern of data is, and then I'll try to decide between whether it fits hypothesis A or hypothesis B. So essentially the idea is you have a hypothesis, it generates a pattern of data, and that means that you could look at the pattern of data and say, well, here's what the reality is. Here's what the hypothesis is said. Now that sounds simple, but the trick is that it's very rare that a pattern of data will tell you, yes, this is the only hypothesis that's compatible with this pattern of data. Usually what happens is you see a pattern of data and you can say, well, if hypothesis A is true, it's more likely to have generated that pattern of data. And if hypothesis B is true, then it's less likely to have generated that data. And then you can say, well, okay, given this data, hypothesis A is more likely, hypothesis B is less likely. So what you do is start out not with just one hypothesis, but with a bunch of hypotheses that you think, some of which you think are more likely, some of which you think are less likely. You go out and you look at the data, and you readjust. Maybe some of the ones that you thought weren't very likely become more likely. Some of the ones that you thought were very likely become less likely. All right, that sounds very abstract. What we've done is to actually give children problems that are like this, problems where we give children a very simple system, like a simple machine. There are a number of different hypotheses you could have about how the machine works. We give the children a pattern of data, and we see if they can use the pattern of data to figure out how the machine works. And just incidentally, part of the reason why we've learned so much about what children know and what they can learn, part of the reason why our picture of children has changed so much, is because we've learned to ask them to tell us what they know in their language instead of in our language. So if you ask a baby what they think about probability, they're not going to sound very smart. If you ask a grown-up what they think about probability, they're not going to sound very smart. And even if you ask a 3-year-old what they think, you'll get a beautiful stream of consciousness story about ponies and birthdays, but you won't get anything that actually sounds like it's very rational. And that was part of the reason why people like Piaget thought that children were so irrational. So how could we ask them what it is that they think? Well, here's what we do is look at what they do rather than what they do based on what they think rather than what they say about what they think. And this very simple device has turned out to be a really good way of doing this with 3- and 4-year-olds. So what we do is we have this little machine, and it lights up and plays music. When you put some things on it, blickets, and not other things, not blickets. And your job is to figure out which things are blickets, and more generally, to figure out how to make the machine go. Now, in fact, the way this little machine works is that there's a graduate student behind the curtain who's pressing a button, who's making it go when we want it to go and not. But fortunately, none of the subjects in our experiments, none of the babies, and none of the adults ever figured this out. So we wanted to see whether children could not only use a pattern of statistical data to decide, say, is A a blicket or is B a blicket, could they do something more impressive? Could they actually find out abstract principles about how this machine works, like abstract logical principles about the way that this machine works in general, independently of the particular blocks? And I want you guys to actually be subjects in this experiment. Here's the way the experiment goes. You see this pattern of data. D goes on the machine and nothing happens, and D goes on the machine again. The D and E and F are different blocks. D goes on and nothing happens. That happens 3 times in a row. Then E goes on and nothing happens. And then we put D and F on together and the machine lights up. And then you put D and F on again and the machine lights up. All right, now you've seen this pattern of data. Now you have to decide which hypothesis is going to explain this pattern of data. So the question is D a blicket?
No.
Is E a blicket?
No.
Is F a blicket?
Yes.
Okay. Okay, you guys are as smart as the undergraduates at Berkeley. Not as smart as 4-year-olds. Because suppose first you saw this sequence of events. So you saw that A and B and C independently don't make the machine go. A and B don't, B and C don't, but A and C together do. And now suppose you went back to that. So if you wanted to explain the sequence of events, how could you make sense out of it? Well, you can make sense out of it if it's actually combinations of blocks that make the machine go. A doesn't do it by itself, C doesn't do it by itself, but the logical combination of A and C together actually makes it go. And now if you went back again and looked at this sequence of events, you might change your mind about whether or not D was likely to be a blicket. Because it could be, if this is one of those AND conjunction machines, then D and F together might be what you need to make this machine go.
But you asked, is D a blicket? And you asked, is F a blicket? You never asked, are any combinations a blicket?
Okay, that's a really good point, and I will get to it in a second.
I teach Bayesian statistics.
Okay, yeah, exactly. All right, so here's what we did. We did exactly the experiment that I just did with you. We did it with Berkeley undergraduates, and we did it with 4-year-olds. And what we did was we first gave them information about the general logical form of the machine. So in this OR training, you figured out what we essentially were telling you is the way this machine works is individual objects make the machine go. And in this AND training, we said the logical principle is that combinations of blocks make the machine go. And then we gave children with new blocks a new test, just like the test sequence that you saw. Now, if you're actually being rational in making these higher order inferences, then you should have a different answer about D and E and F if you think that it operates on this AND principle or it operates on this OR principle. And we know from lots of other work that adults tend to assume that this OR principle is the way that artifacts and machines like this work. To the extent that adult theories of causal inference in adults often just assume that this is the principle that everybody has to use to solve this problem. Okay, so here's the result of this experiment. When we looked at the OR case, the obvious case, the more likely case, both the adults and the children got it right. They said that F was likely to be a blicket, but D and E were not. But when we looked at the AND case, the 4-year-olds were actually much more likely to get it right than the adults were. So in fact, for the adults, there was no difference between the AND and the OR case. It was as if they just weren't paying attention to this data that went against their deeply ingrained assumption about how the world should work. And when we did the same experiment with 4-year-olds, on the contrary, the 4-year-olds were actually paying more attention to the data. They were actually being better learners, and they were willing to shift their idea about how it worked based on the new data, and they could discover this unlikely hypothesis about how the machine worked. Now, David, in answer to your question, maybe this was just something about blickets, about how we use the word blickets. So instead of asking the children and the adults, is it a blicket or not, we actually asked them to make the machine go. And then we measured whether they used two things to make the machine go or they used one thing to make the machine go. We found exactly the same pattern of results. So that the children were likely to, in the conjunction case, to use two things, in the or case to use one thing. The adults always just used a single object to make the machine go, whether they had information about the conjunction or not. And let me just show you a little clip, because as developmental psychologists, what we do is to show cute pictures of babies or little kids. Oops.
Oh, you need sound?
What should we call this one? Square. And what should we call this one? Ball. Sounds good. Okay, so let's see what happens when we put triangle on the machine. Are you ready? Let's see. Look at that. The machine did not turn on. Let's see what happens when we put triangle on the machine again, okay? Look, the machine did not turn on. Now let's see what happens when we put triangle on the machine one more time, okay? Let's see. Look, the machine did not turn on. Now let's see what happens when we put square on the machine, okay? Look at that. The machine did not turn on. Okay, now let's see what happens when we put triangle and ball on the machine together. Look at that. The machine turned on. Now let's see what happens when we put triangle, square, and ball all on the machine together. Are you ready? Let's see. Look at that. The machine turned on. Okay. Now let's see what happens when we put triangle and ball on the machine together. Are you ready? Let's see. Look, the machine turned on. So Scarlett, do you think that triangle is a blicket or not a blicket? A blicket. And do you think that square is a blicket or not a blicket?
No.
No.
Which makes it face.
And do you think that ball is a blicket or not a blicket?
Yeah.
Yeah. Okay, so Scarlett, which of these should we use to make my machine turn on? Those two? Yeah.
Okay, so this is nice because you can see how bright-eyed that little girl is. But also, if you were like me, you would have a really hard time figuring out what was going on yourself. I actually showed this to David Dobbs, who's a science writer at the New York Times, and he sat and looked at it and said he had no idea what was going on with the blocks and the detector. It's actually really hard to keep track of, even if you're an adult. But these 4-year-olds were not only keeping track of it, but they were drawing the right conclusions about how the machine would work. Well, now we've done at least 2 other experiments now. When we first did this, we were sort of shocked. We've done at least two other experiments with totally different materials in which we find exactly the same pattern. If we are trying to teach you an initially unlikely hypothesis, one that doesn't look very probable from an adult perspective, the children are actually better than the adults, and young children are actually better than older children at solving those problems. Okay, now I'm going to shift gears for a minute and talk about why it is that might be true. So it seems very counterintuitive. Why would little kids actually be better at solving these problems than adults? And remember all those people who thought that we were the great rational thinkers and children were irrational. Well, let me go back to that Bayesian idea. So I said the Bayesian idea is that you could think about having a whole bunch of different hypotheses and having what scientists would call a probability distribution over those hypotheses, thinking some of them are more likely and some of them are less likely. So you have a whole bunch of different hypotheses, you have different probabilities of those hypotheses. If I give you 2 hypotheses, you can figure out what the probability is of each hypothesis given the data. But here's the problem. The problem is, of course, there's very, very large, in some cases an infinite number of possible hypotheses that could be compatible with the data. How do you decide which ones to test? So if I give you 2 of them, you might be able to say, yeah, this one's more likely than the other. But if you're going out of the blue, how do you even decide which ones to think about or which ones to consider? And in machine learning, the way that they solve this problem is by a process called sampling, which means you just look at one or two or some small sample of the hypotheses, you compare them to the data, then you update your probability distribution, then you take another sample and you update, and you do this in this iterative kind of way. And a very interesting thing that comes out of this kind of work is that there's two different ways that you could think about trying to do this search, and this actually goes back to Louis' talk. Because the way that people think about this is in terms of this idea of temperature, like those molecules that were jumping around. So imagine that you think about this as if there's a big box full of hypotheses, and you're sitting at some place in the box, and you're trying to search to decide which hypothesis to test. Well, one thing you could do is you could do what they call cold, a low temperature search, which means you just don't look very far from where you already are. You take the hypothesis you already have, maybe you tweak it a little bit around the edges, you change it a little bit, you see, okay, does that do a better job of explaining the data, or should I really stick with where I already am? And if you get to one that sort of seems to be doing a better job, you stick there and you don't change very much. An alternative way that you could do the search is a high temperature search. That means you bounce around that space like a molecule bouncing around a box at high temperature. You might try something that's really bizarre, that's really way off there, off into a corner. And you might get a little data that supports that, but not really enough to make you want to stay there. So you go bounce off to try and find some other idea, test this other kind of idea. Now, each of these ways of doing the search has advantages and disadvantages. If you do a low temperature search, you're more likely to get an answer that's pretty good pretty quickly, but you might miss something that is actually the really good answer that is initially not something that you thought about very much. So you can get stuck in what scientists call a local minimum. You could get stuck just kind of finding the almost okay solution and never find the really, really good solution that's out in the far parts of the space. On the other hand, if you do a high temperature search, then you might get to the really good, unusual answer, but it's going to take you much longer. And while you're bouncing around trying all of these things that actually aren't going to turn out to be right, if, say, a mastodon is charging at you, and your hypothesis is about how best to deal with this mastodon, you are not going to be very good at actually functionally coping with the world. So if you want to actually functionally cope with the world, a low temperature search is better because it'll give you a pretty good solution pretty quickly. But if you want to explore the world, if you want to find really unusual solutions or unusual hypotheses, a high temperature search is better. And the way that in computer science, at least one discovery that people have made about how do you combine the advantages and disadvantages of these two ways of searching is you start out with a high temperature search. So you start out exploring a lot, looking at a lot of different possibilities, and then you do something that they call simulated annealing, which means you cool off. So you start out with a high temperature search, you look at lots and lots of different possibilities, and then you narrow it down to the things that you think are most likely to actually be successful. Okay, so here's our hypothesis. Our hypothesis is that children are doing this kind of high temperature search, and the adults are doing a low temperature search. And that makes sense out of that data that I just showed you about the liquid detector. So if children are actually looking for unlikely alternatives, more likely to do that than adults, if they're doing that, they'd be more likely to do that if they're doing this kind of high temperature search. And what that means is that they do better, but they'd only do better in cases like the AND case, where the answer is initially something that's unlikely. They wouldn't do as well in cases where the answer is something that actually is going to be more obvious. And by the way, one of the things that we did in the experiment was we had a condition where we didn't give any training at all. We just gave the ambiguous stimulus, like the one that you first saw. And it turned out that in that case, the children actually were also likely to think that the OR case, the OR answer was more likely. But they were more willing to shift to something new when they had more data. So one possibility is just that the children know less than we do, and that makes them less biased towards certain kinds of answers, and that's probably part of what's going on. But even when they start out with the same biases that we have as adults, they seem to be more willing to shift and move and try something new than the adults do. And I like this idea about the high temperature search because it actually explains some things about how children will just look about some of the reasons why we might have thought that children were irrational and peculiar in the way that they reacted. And let me show you a little tape of a child in another Blicket detector experiment. And in this experiment,
this makes that light up the box.
the experimenter first showed that red made it go and yellow didn't, and then showed an anomaly, the yellow one that didn't, and asked the children to just explain it.
Oh. Nothing. This one's lighting up, and this one's not. So that means making this light up. Oh, it's because this needs to be like this, and this needs to be like that. That's why. Oh. The boxes are the wrong way.
This is his suggestion to the experimenter. The box is the wrong way, so let's move this other one over.
What should we do?
Oh, because the light goes only to here, not here. Oh, the bottom of this box has electricity in here, but this doesn't have electricity. It's lighting up. So you need to put 4. So you need to put 4 on this one to make it light up, and 2 on this one to make it light up.
Okay, so aside from the fact that that little boy is incredibly cute, it turned out that what he was doing was actually quite typical of what children did in this condition, in this experiment, where you gave them something that didn't make sense and asked them to explain it. They would generate, in the course of just a few minutes, all these different hypotheses. And not only was he generating many different hypotheses, but he'd quickly veer from one hypothesis to the next with just a little bit of data. So in some ways, he's looking like a terrific scientist. He's generating lots of ideas. In other ways, he's looking like a terrible scientist because he isn't actually taking the time to go through every single hypothesis before he tries another one. He's bouncing around from one idea to the next. Since I think I'm almost out of time, let me just say this make this one last point about this. One of the interesting puzzles about children is why it is that we have children at all. Not the obvious proximal reason, which presumably everybody in this room has figured out, but from an evolutionary perspective. Why do we have this long period of completely helpless immaturity? In fact, arguably, children are not only useless, but worse than useless because we have to put so much time and energy into taking care of them. And in fact, for human beings, our period of immaturity is much longer than that of any other animal by a very substantial margin. What would be the evolutionary explanation for what seems so paradoxical? Well, if you look across many, many, many different species of animals, what you see is this correlation. And the correlation is that the longer the childhood of the species, the bigger the brain and the smarter the animal. So if you compare, for example, crows, this is actually a New Caledonian crow on the cover of Science who's learned how to use these hooks, to chickens. The crows are incredibly smart animals, as smart as primates. The chickens are incredibly dumb animals, very good at pecking for grain, no good at doing much of anything else. These New Caledonian crows are fledglings for as long as 2 years. The chickens are mature within a couple of weeks. And that's not just true about crows and chickens. It's true about mammals, marsupials, essentially all of the animals that we know in the and in fact, when you look at fossil evidence, even compared to Neanderthals, our period of immaturity increased during the period when our cognitive capacities increased. So here's the conclusion. I think that childhood is evolution's way of doing simulated neuron. So childhood actually is designed from an evolutionary perspective. Our human childhood is designed to give us this protected period, this period where we don't actually have to do anything, where all our actual decision-making is being taken care of by adults, and all we have to do is to do this kind of wide-ranging exploration of unlikely possibilities. So another way I like to put this is you could think about children are really the research and development division of the human species. We're talking about it here at Silicon Valley. And we're production and marketing. So they're the ones who get to do this kind of wide-ranging exploration every day just as part of their normal everyday life. And we grown-ups get to do it sometimes when Piero invites us to come to one of these lasers.